Okay, let's start. So in the previous lecture, we were looking into making our amplifier, right? Making our amplifier to obtain power gain. And we saw that if the stuff inside the box is a MOSFET, which the characteristics, which is well known, that is I1 equal to 0, and I2 is equal to beta by 2, V1 minus threshold voltage whole square, or the linear current equation, right? So we had to do two things. We had to ensure that the input is biased to ensure that we not only apply the input directly, but we also had to ensure that we had a DC voltage, because we wanted to establish some V1Q at the input port. Similarly, it was not sufficient to simply connect the load resistance RL directly across the output port, because we had to honor the output side condition of transistor being in saturation, right? So we had to honor the fact that V2 should have been at least higher than V1 minus 1 threshold voltage. So if we had to honor that, we understood that we have to basically put the load resistance in series say V2, this is applied, and this is V1 applied. And the V2 applied should be such that in the presence of an output current I2Q, the voltage at the output port should be V2Q such that V2Q is greater than or equal to V1Q minus 1 threshold voltage. Right, so this is where we stopped in the previous lecture. You might be wondering, some of you might be wondering why I have not yet put the block diagram of a MOSFET inside the box, and I am dealing with the box. The reason I have not done that, we'll do that in this class. The reason I didn't do this is because I wanted to I wanted to impress upon you the fact that this box is a generic box, right? MOSFET is a particular vehicle for which we are making the amplifier, but the stuff inside the box could have been a BJT, a FinFET, a CRT, right? A vacuum tube, or any device with a certain type of IV characteristics for that matter. So whatever be the device, there are certain characteristics which are common to this box. So the reason I didn't till now replace the box with a MOSFET was basically to impress upon you the fact that if I give you a device which does not have this characteristics, does not necessarily obey this square law model, but obey some other model, you should be able to generate the biasing network and apply the input and take the output appropriately, while respecting the requirements of the box. Okay, so again, the structures that we are familiar with are not necessarily particular to a MOSFET. It can be particular. The concept behind this is quite generic, but how you need to bias will depend on what are the particular properties of the nonlinearity inside the box. Okay, so having said that, now we can move on. Now we can move on and then replace the box with our symbol of a MOSFET, and then proceed. Okay, so in that case, we already saw that this was our box, right? And if this is the MOSFET, this is the input terminal V1, this is the output terminal V2, and we have applied the input. Questions? Okay, so so now we can also replace these terminologies V1 and V2 with the more popularly used terms. That is, this is the gate voltage, this is the source voltage, that is the source terminal, and this is the drain terminal. Right. So going forward, we'll be using gate, drain, and source instead of V1, V2, and I1 and I2. Similarly, this current is IDS because this current is the current that is flowing between the drain and the source terminals. Any questions? You can interrupt me. I mean, no problem. So input current IG is equal to 0, right? Okay. So now let me sketch this stuff in a more conventional way that you more often than not see in books. The more conventional way to sketch this is not to have RL in the way that we have shown here. So RL goes between some supply, which is more conventionally called VDD. The input is now between gate and the source, and we can be redrawn like this. This is, let's call this VGSQ because the Poisson input is being applied between the gate and the source. And the output is now taken across. So in this case, in the block diagrammatic case, where was the output taken from or across? Across RL, right? So we were taking the output across RL in this case. So similarly here also we take the output across RL. So this becomes V0. Now could you comment if I take the output like the one that I have shown in this figure and instead I take the output like this, let's say V out. What is the relationship between this V out and VO? Right. So incrementally, can you comment what will be the relation between VO and VO? Right. So incrementally, V out will be minus V0, right? So more traditionally, we always say that the output is taken between the drain and the not the source particularly, the drain and the ground. The reason we take it with respect to a ground is because we seldom have a floating source. In most cases, you don't have access to two terminals of the, sorry, I didn't mean source. I wanted to mean the load. You seldom have access to two terminals of the load. What do I mean by that? I essentially mean if you have an RL, you almost always don't have access to both the terminals of the load. you have access to one terminal and the other terminal is implicitly grounded. The reason being, in most cases in circuits, you will see that the load is not an actual RL, it's an implicit RL. By implicit RL, I mean it's probably the input impedance of some other stage. The input of some next stage. Maybe you have maybe this amplifier is driving another stage, which has some input impedance, right? And this impedance, when you are looking into the input of the amplifier, will, and the way you calculate it, will be a Thevenin impedance looking in. So when you are calculating an impedance, which is Thevenin impedance looking in, what is the other terminal of the Thevenin impedance? It's ground, right? So that's why, in order to make this analysis generic, we almost always try to take the output between whichever node you think will be the output terminal and the ground, right? So in this case, the ground happens to be the source, so we take it between the drain and the source. Okay. Okay. So now, if RL is supposed to be taken, if the output is supposed to be taken between the drain and the source, which means that RL is, you cannot essentially put the RL between drain and the VDD, because this implicitly assumes that you have access to both terminals of RL. One terminal you have connected to VDD, other terminal you have connected to the drain, right? So if you don't have access to that, which means you probably have an RL like this. So what should you do in order to ensure that this RL is not there? Now, what should you do to ensure that you take the output across RL while maintaining the transistor in saturation? Is the question clear? We cannot put the RL between drain and the VDD. You can always have to ensure that the one terminal of the RL is grounded, which means you have access to only one. So now I want to still get an amplification across RL. So what should I do? We come to capacitor, right? So there is a reason why people connect capacitor. And so what is the thought process behind it? So what is the first step that you should respect? For, again, going back to whatever we have been discussing in the last couple of classes, for the amplifier, for this device to work as an amplifier, you have to bias it properly, right? So how should I ensure? So biasing has two aspects to it in a two-terminal device: input bias, output bias. Is the input bias fine? Do we have to change anything on the input side? Input bias, you don't have to change anything, right? Because I haven't affected the input terminal at all. Okay. And changing the output terminal doesn't change anything to the input terminal, because there is an isolation between the output and the input. Whatever I do to the output doesn't change the input. Okay. So now we have to see whether we respect the biasing condition at the output terminal. So what should I do to ensure that the transistor is biased in saturation, because it's not in cutoff as long as we ensure that the input terminal bias is fine. So in output terminal, I need to ensure that the transistor is in saturation. So what should I do? Where? Okay, so where should I apply the battery? I should between drain and RL. Okay, that's great. So I should apply a battery, something like this, right? So I have essentially interchanged the position of the battery and the RL, right? This will work. But I have another issue. The other issue is that you also don't have a floating battery. That is a practical problem. Just like you don't have a floating RL, you don't have a floating battery, because think about it from the perspective of an integrated circuit or an IC, right? The IC that make up a cell phone, or you see in your labs. What are they? They are also kind of black boxes with some leads coming out. And maybe one of the terminals of the lead is the supply, right? Because it's VDD. Maybe some other terminal is a ground. So when you put a battery, what do? You put a battery between these two terminals. You don't go inside the circuit and put a battery between two terminals, right? So essentially what I'm saying is, just like a load, you don't have access to both terminals of the battery. You have only access to one of the terminals. So neither the load nor the battery, you have access to two terminals. Again, this is a practical problem. This is not a theoretical problem. Okay. So if you had the access to both the terminals, then you could have done this. But the issue is, you again don't have access to both the terminals, so I cannot do this. So this also cannot be done. What I essentially mean that, just like you have a load connected to ground, one side connected to ground, you also have a battery whose one side is connected to ground. So you have to make do with one terminal of the battery, because other is a reference. So now guide me through what can be done. Oh, where do you get current source requirements here? It's not very obvious, right? Why should you have current source? Another resistance where? Drain to VDD. Okay, yeah. I mean, I can have a explicit resistance that I can definitely have. So let's put one node resistance here. So VDD. So this doesn't violate any condition, because RD can be an explicit resistance that I put in my design. When I put an explicit resistance, I have access to both terminals. So that can be done. Okay, so I put another resistance RD, fine. So now what? But I need the, okay, so after putting the resistance RD, I have to see whether the transistor is in saturation or not. Right? Moment to change anything, you have to go back and see whether the biasing has changed or not. So how do I establish whether the biasing has changed or not? What should I check? Condition of saturation, which means that you, just like before, you assume like the transistor is in saturation. You find out IDSQ. If the transistor is in saturation, IDSQ is only dependent upon the input side, right? Input side condition. That is, if the transistor is in saturation, IDSQ should only be equal to proportional to VGS minus VT, base threshold voltage whole square, right? Or V1 minus V threshold voltage whole square, like we did in the previous lecture. So if that is true, then we can adjust the values of VDD and RD to ensure that the transistor is in saturation if the transistor is already not in saturation. Okay, so that can be done, that we know. We already saw it in the previous lecture. What needs to be done if this is not in saturation? VDD has to be raised or RD has to be decreased. Those things can be done. So this is as far as biasing is concerned, but it still doesn't solve the problem, because we want the amplification across B0, across RL, and one terminal of the RL is still floating. We haven't done anything. So how do I get the amplification across B0? Okay, capacitor between drain and the floating terminal. Okay, that's one definitely a solution. But what if I just say that? What if I simply connect? So before I connect anything, now we are talking about this gain that we are talking about is a small signal gain, right? It's an incremental gain. In the incremental picture, I'm supposed to have the gain, right? So in the incremental picture, how do I establish whether I have gain or not? We have to replace the transistor with its incremental equivalent, assuming it is in saturation, and then sketch and then establish whether we can have a gain or not. So in the incremental picture, what is going to happen? In the incremental picture, I'll replace the transistor with its incremental equivalent. And the incremental equivalent was Y21 times VGS. On the input side, you have PI, resistance. This is floating, right? VGSQ has gone to ground. This is VG. And the way I have sketched the circuit till now, this looks like RD to ground. And I have a resistance which is sitting here, right? So in the incremental equivalent, where do you think I can connect this resistance to so that I get some gain? I can connect, yeah, so I can definitely connect it to the drain, but can I connect it to here? It will be shorted, right? And I cannot also do this. I cannot also do this. Can I do this? Why can't I do this? But this is a incremental model, right? In the incremental model, I don't bother about bias. Biases are all gone to zero. Yeah, right. So essentially, what I presume what you're implying is, even though in here it looks like since there is no voltage source anyway in the incremental equivalent, we don't have sufficient information to tell that whether the biasing picture of this will be appropriate, right? So as we said that if we have to translate it to the biasing picture, if you have to translate it here, then again we'll have the same problem, because even though in the incremental picture, RL looks to be connected between a ground and some terminal, in the biasing picture, I'll have to insert VDD within this loop somewhere. Correct? So moment we say that we have to insert VDD within this loop, either one of the two things will happen. Either VDD requires a floating terminal or RL will require a floating terminal. Right? So which means that this contraption will, even though it looks like it's fine in the incremental picture, will not be sufficient in the biasing picture. Right? So this cannot be done. So what else can be done then? So I have the RL here. Now connect what to the drain terminal? Right. You can connect the floating part of the RL to the drain terminal. We can connect the floating part to the drain terminal, because with the assumption that I have access to both the terminals of RD, right? Because so instead of saying those things, let me show you what I mean. So if I have to draw an equivalence between these two networks, the picture on the bottom is incremental, picture on the top includes biasing. So if they have to be equivalent, what should I do to RL in the top? Connect it to the drain, right? So connect it to the drain. Right? If we connect it to the drain, then it seems like, I mean, I have honored all the floating condition, I mean, right? All the floating issues, in the sense that your RL, you don't need access to two terminals of RL, neither do you need access to two terminals of VDD, right? And it seems like in the incremental model, in the incremental picture, if I take the output across RL, right? If I take the output across RL, what will be V out? What will be the incremental V out? right? So it should be minus Y21 VGS, minus Y21 because the current is direction is pointing downwards, times RD parallel R, right? So as long as I can ensure this, that the Y21 times RD parallel RS is more than 1, we have gain. Okay, so so it seems like it's fine, but do you see something wrong in the top picture? Think from the perspective of biasing. So what was the requirement? In first requirement was in order to establish the fact that we require an IDSQ current, we had to establish the transistor was in saturation. And before we connected RL to the drain, this IDSQ was coming through the VDD. Right, so the path was this. So now after we connected RL, what do you think is the problem? Right, the quiescent point can change because if I do a KCL at this drain node, what will I observe? I should observe that some part of the current, let's say IRL, some part of the quiescent current IRL will go into RL, which means this current will be, it is moving around so much, minus IRL. Right? So the quiescent point can change, and it is also not necessary that the IDSQ that you had after, it is also not necessary that IDSQ that you had after, before applying the RL will be the same, because if the quiescent point changes, the transistor can likely go out of saturation. If the transistor goes out of saturation, then obviously the equations that you used to come to the value of IDSQ will not hold. The equations will change. You have to use the linear region equation, which naturally means the solutions of the solutions for IDSQ can be different. What I'm essentially pointing to is that the entire output side will be a mess, right? So you probably initially thought that when you were designing a circuit, you had something in mind. You had sized your network. You had put the biasing in such a way that IDSQ was supposed to be exactly 1 milliamp or 2 milliamp or whatever. But the moment you connect RL, IDSQ might not be even the same, right? So it's likely to go out. It can likely become a problem. So if it's a problem, then we have to then address it. Again, what I'm trying to say is that it's not necessary that just by putting RL it will always be a problem. What I'm essentially trying to point out is that it is likely to become a problem. So can you help me understand that, whether you understand that statement? So, or in other words, what I'm saying is that putting an RL like this need not necessarily cause a problem all the time. Can you think of a case in which putting an RL like this will not necessarily cause a problem? Right. So the trivial cases, RL is infinity. If RL is infinity, then there is no current division, you are good, right? Now, infinity means open circuit. One might say that if it's open circuit, I'm not driving anything, then what's the point of designing anything if I'm not driving RL? So let's assume we are driving some RL. What is infinity? Infinity is something which is very large with respect to something, right? So what is it that RL has to be much greater than in order to ensure that putting an RL doesn't affect the quiescent? Somebody said something about drain voltage, right? RL has to be much greater than RD, right? So why do you think? Yeah, that is correct. That is indeed correct. RL has to be much greater than RD, but why? Among all the theorems and everything that you know about circuit theory, or even not theorem, the basic fundamentals of network theory, what are you implicitly saying when you are saying that RL has to be much greater than RD? Can you just raise your hand and answer? I can't see who is answering. Okay, yes. Exactly, right? The current always wants to go into the lower resistance path, right? I mean, why current? Why blame current? All of us want to, right? You always want to take the path of least resistance. The same as current. So if a current division has to occur, most of the current would like to flow into the least resistance path. And the problem here is if R is resistance, I mean, much lesser than RD, right? So whatever is the IDSQ that would have come out of the transistor, most of it would have liked to flow into RL and not through RD. And that would have affected the biasing. Ultimately, whatever current that flows out of the transistor needs to flow through RD in order to ensure the biasing is not affected, right? So which essentially means that if you have size RD, let's say RD is, I don't know, maybe 10 kilo ohm, you have to ensure that RL is much greater than 10 kilo ohm so that your application of the RL does not affect the biasing. Okay. So, but in most cases, RL is not in your control, right? Just because you require RL to be much greater than something doesn't necessarily mean that you will have that. Then one might say that if RL is not, if a condition comes where RL itself is, let's say, 1 kilo ohm, then obviously you cannot do this. Then you might turn around and say, in that case, I'll probably ensure that RD is, let's say, much less than 1 kilo ohm. Let's say RD is 100 ohm. So then probably you will also be right? So this, yeah, you will be able to size it appropriately. But what's going to happen if you keep on reducing RD? Pardon? Yeah, biasing point will disturb, but I mean, if I keep on reducing RD, for example, if I take the trivial case of RD goes to 0, will the transistor be in saturation? Let's say RD is 0, which means it's short. Will the transistor be in saturation?
No, we cannot comment until
RT is 0.
No, for saturation.
No, we initially assumed that idea in the absence of RL, it was in saturation. Then obviously, yeah, right? So if I connect VDD directly to the drain, it is in saturation, right? So again, RT0 is a really trivial case. Small RD will be, I don't want to make RT0, I'm saying RD is smaller than whatever it was initially. Transistor will be in saturation, but what is going to get affected? The gain, clearly, because it's a parallel combination between RD and RL, right? So you are losing out on gain. So essentially the reason I'm harping on this is to, through this example, I'm trying to address the fact that you will have to make decisions when you are making a design, and it's not necessarily that you'll be making a design of a circuit that is known to you all the time. In fact, the whole purpose of a circuit design is the goal is that you'll be going out and making the circuits which you have never seen before. So the thought process should be such that you should be able to understand the trade-offs on the fly. Okay, so now if this is not something that you can do in a most generic case, so which essentially means that I have to keep RD as high as possible, right? So we need to keep RD as high as possible. So if I want to keep RD as high as possible, because I want to honor this condition, right? I need to honor the fact that RD parallel RS does not drop, right? So then I cannot always connect these two together. Correct? Okay, fine. So then if we cannot connect these two together, then we have to find out a solution. I mean, some of you already alluded to it, but let me try and approach it from another vantage point. What I am trying to allude to here is that I can arrange some value of VDD, arrange for some value of VDD and some value of RD, with RD being as high as possible, and still ensure that the transistor is in saturation, right? So, and what will be the condition? You have to ensure that VD is greater than VG minus threshold voltage. As long as I can ensure that the transistor will be in saturation, right? And this can be arranged. I mean, if VD is lower than what you expected, then you raise the VDD, right? And yeah, automatically the drain voltage will go up. Fine. So this is as far as the biasing picture is concerned, we can do this. But what is the root cause of RD loading the quiescent picture? What is the root cause? The root cause is the voltage here at these two nodes, this voltage, that is VDQ, and the voltage across RL are not the same before we connect them. Right? What is the voltage across RL before we connected them? 0. Right? So now naturally, if I connect these two together, I am connecting two nodes with the different potentials. So their current will flow into that node. So if I don't want the current to flow into the node, what do I need to do? I need to ensure that they are of equal potential to begin with. Correct? So how do I make them equal? So, I mean, I don't know why you say capacitor straight off. It's not particularly obvious to me why should be capacitance. As a layman, what I would do is I will just simply, if I have to raise 0 to VDQ, I'll put a battery of value VDQ. Right? So if I put a battery of value VDQ, then if I connect these two, then I don't have a problem anymore. Correct? But therein lies the problem that I don't have a floating battery. Right? So even though this will work, I don't have a floating battery. So this is not a practical solution. So therein lies the fix which some of you were alluding to, is the fact that since a battery, so what is a battery? A battery is a VBAT. A battery by definition is a source of infinite charge. Right? So what do I mean by that again? If I have a current source or some load, right? I'm modeling the load as a current source, which is I0. If I have connected it across the battery voltage doesn't really change. Right? An ideal battery, the voltage will retain itself. So even let's say I wait for some time t, right? Let's say I wait for some time t. How much charge am I pulling out of the battery? I0 times t, right? So delta Q from the battery will be I0 times t. And even though I have pulled out I0 times t, the voltage across the battery hasn't changed. Right? That's an ideal battery. So it's basically a storehouse of infinite charge. Among the elements, the basic elements that we know in circuits, storehouse is charge storehouse is a capacitor. But what is the difference between a battery and a capacitor? Let's say it has some charge Q initial, and I do the same experiment. I put I0 like this, and I get after some time t, the amount of charge that I would have pulled out would have been I0 times t. So the voltage across the capacitor would have dropped from Q initial by C, let's say this is C, to Q initial by C minus I0. Let me call this delta Q. Right? If we want to use a capacitor like a battery, what constraint do I need to satisfy? I need to satisfy that delta Q is much lesser than Q initial, and under that, and Q initial is what? Q initial will be the value of the capacitance times the V bat, right? Whatever battery voltage, whatever voltage you are trying to down. Now, given that V bat is a finite value, right? Maybe 1 volt, 2 volt, 5 volt, whatever it might be. Then if you have to ensure this condition, delta Q should be much, much less than Q initial. You have to satisfy two things, one or two things. One is, what is delta Q? Delta Q is I naught times T. You have to either satisfy that T is not large enough so that you are not pulling out. If you, so T is not large enough, or I naught is very small, or T is not large enough, or the other condition is that seek has to be infinitely large, right? If the C is infinitely large, then you don't have a problem. If C is infinitely large, Q initial is itself infinite, and I naught times T is finite, right? Since I naught times T is finite, delta Q is finite, but Q is initial will be infinite, then it's essentially almost equal. And the voltage across the battery will, capacitor will be Q initial by C, right? So one of two conditions. The conditions is if C tends to infinity or T tends to 0, right? We will ensure a capacitor operates like a battery. Okay. So this C tends to infinity is not practically realizable, right? Obviously, you cannot make anything infinity. But can this T tends to 0 be realized in our context? So again, what I mean by that is, when I say T tends to 0, in this picture, I assumed it's a constant current source. It's a DC current source. Okay. But let's assume this I naught is not a DC current source, because if you have a DC current source, ultimately, if you have a finite value of capacitance, however large it is, it will drain it out. Maybe not after 1 second, maybe after 1 hour, maybe after 1 day, but it will drain it out. In case of an ideal battery, it will not be able to drain out. So however large your capacitance is, as long as the value is finite, you cannot replace the capacitor with a battery, right? So I hope that statement is clear. Okay, so if that statement is clear, what I'm essentially saying is that if I naught is a DC current source, or if you are drawing out DC current out of a capacitor, then you cannot hope to have a capacitor replacing a battery, because ultimately, after some time, the capacitor will drain off, right? So this is not a solution if you are planning to use a capacitor to replace a battery where the current is DC, right? Because you'll not be able to honor this condition of T tends to 0. However, let's assume I naught is not a DC current source, and I naught is a, let's say, a time varying current source, right? So maybe I naught goes something like this, so on, right? Okay, so let me call these nodes as, let's say, T1, T2, T3, and so on. So now, can you comment on what should I? Can you comment on should I be able to replace a capacitor with a battery, or rather, should I be able to replace a battery with a capacitor? In principle, it's not a DC current source anymore. Maybe under certain condition, yes, or or no. Yes. Okay. Why yes? Why yes?
should be very small. It is again charged.
Correct, right? So what is delta Q in this case? In this case, the delta Q cannot go to infinity, even if you go observe it for infinite time, because this is I naught, right? Because I naught is increasing, then it is decreasing back. So what is delta Q? Delta Q is always the area under the curve, right? It is sometimes positive, sometimes negative, sometimes positive, sometimes negative. As long as this delta over a period of time, delta Q is 0, which means the area on the upper half of the area on top is equal to area on the bottom side. Delta Q doesn't diverge to infinity, right? So what I essentially saying is that if this is a zero mean signal, right? If I naught is zero mean, then delta Q will always be finite. Maximum delta Q will always be finite. Is that fine? Since maximum delta Q is always finite, then there is a chance, right? If I can make C to be large enough, now infinity is not required. If I can make C large enough, then I can replace a capacitor, replace a battery with a capacitor, because then I can ensure this condition. Right? Make sense? What is the condition? The condition is that I naught has to be zero mean signal. If I naught is not a zero mean signal, your delta Q can diverge to infinity if you wait for sufficiently long time. Doesn't seem that you are convinced. So why don't you push back? Ask me something. Why do you are not convinced?
But it won't be applicable for what type of.
Yeah, it has to be for zero mean signal. Yes. Pardon? Capacitor has to be charged initially because that's what we assume, right? It has to have a Q initial charge. Yes.
So in the problem that we used to do earlier,
Yeah.
this had a zero mean signal at the current whenever we applied.
Yes, so that the problems are implicitly set like that. Right? So, but if you, what I'm trying to say is that if, let's say, sometimes we make the statement that the infinite capacitor acts as a short circuit, and infinite capacitor acts as a short circuit because underlying assumption is that the signal that it's trying to process is not zero mean. Right? So if the signal has a DC component, regardless of the fact that how large the capacitor is, the signal will not flow through. So zero mean means zero DC. What is the mean of a signal? Mean of a signal is the DC part of the signal. Right? The current cannot have a DC part. That's all it means. Okay. Any questions? Any doubts? Okay. So if this is true, then if I go back to our configuration. So for things to work, we had to ensure that we had to insert a battery of VDQ between the RL and the drain, but then we saw it is not possible. Now we are arguing that this probably is possible as long as we put a capacitor, because we have access to both terminals of the capacitor. That is number one. And number two, if C tends to infinity and we are not interested in processing a DC signal, then this should be possible. Right? So that's essentially the crux of the matter, right? So as long as C, so if I just write into the form of impedance, the impedance seen by the capacitor, right, offered by the capacitor for a signal, if a current let's say I at omega naught is flowing through the capacitor. The impedance offered by the capacitor is 1 by j omega naught times C, right? And the voltage that it will accrue will be some I naught by j omega naught times C, right? So this also is a function of omega, right? So if C tends to infinity, the voltage drop across the capacitor is 0. That's what we mean by when we say that the capacitor acts as a short circuit when C tends to infinity. Naturally, from this expression, it is also evident that regardless of the fact that omega naught, however large it might be, as long as it is finite, the value of the capacitor can be as large as you want, as long as it is finite. If omega naught goes to 0, it will act as an open circuit because 1 by j omega naught C is 0 if C is infinity, if C goes to 0. Okay, so that's essentially the crux of the matter. So the implicit assumption is that we are not interested in amplifying a DC signal. We are interested in amplifying a time varying zero mean signal. Okay, so that's what we were interested in observing across RL. What will happen to the, let's assume the signal, this ID, whatever is coming out of the transistor, has a zero mean. What will happen to that zero mean part? Sorry, I'm making a mistake. So let's assume that this current ID has a non-zero mean. Right? If the current ID has a non-zero mean, what part of that non-zero mean, or rather, the part of the non-zero mean, where will it flow into? Will it flow to the capacitor in the configuration that I have shown you? So this is what you have. Like, this is the circuit, right? So your transistor doesn't know whether you're doing Poisson calculations or not, right? So what I'm essentially saying is that let's assume ID has non-zero mean. If ID has non-zero mean, which means I can express ID as some I DC plus some I AC, where AC is the zero mean signal. So where will that IDC flow? Through RD, right? So that's what, essentially I'm telling you the same story in different ways, right? I'm harping on this because I will not harp on this later on. Okay, so the IDC will flow through this, and it is, as long as now, the IAC part of it can flow either through this, some part of it, and some part can flow through this. Because under AC condition, the capacitor acts as a short circuit. When it's a short circuit, you have the current has both ways to go. It can choose to go either into RD or into RL. Okay, fine. So now that we have established this, the next thing to see is to try to figure out what is this infinite capacitance. You cannot really put infinite capacitance. What should I replace the capacitance with? So in order to do that, let's try to understand what do I mean by infinite capacitance. If I replace again the small signal model of this circuit, what do I get? So this is a small signal equivalent of the network times Y21. So I'm interested in figuring out is there a constraint on the capacitor such that the capacitor behaves like a short circuit at the signal frequency, assuming that signal frequency is not DC. Obviously, it's not DC, otherwise incremental model, there's no point in putting a capacitor. A DC capacitor would have been open. Yeah, C must be very large. Now, C must be very large with respect to what? Infinity is obviously a solution, but when you are designing a practical circuit, you cannot hope to put an infinite capacitor. I need to figure out what is the limit, what is the constraint on C. In order to figure out, I need to understand what am I trying to minimize or maximize. Pardon?
We are trying to minimize the impedance.
Right. We are trying to ensure that the goal is to ensure that this contraption mimics the case in which I don't have the capacitor. Right? In the incremental model, what I'm saying is I'm trying to ensure, if I only scale the output side, this is Y21 times VGS. I'm trying to ensure that this guy mimics this. Right? So we are trying to ensure the equivalence between these two. What is the value of capacitance so that the presence of the capacitance doesn't really affect the incremental operation?
Very high than 1 by R.
Right. So in this case, which means essentially means what I am saying, what we are trying to see is that this current is anyhow flowing out. Flowing out into this. This current is anyhow flowing out into the flowing out or into the contraption. Correct. So what I am essentially interested in is to figure out this loop that I have, right, behaves like this loop. If these two loops are equivalent, then we are good. Correct. So under what condition will these two loops be equivalent? So clearly both the loops are what? Two resistances in series and one capacitor in series. Correct. So what we are essentially saying is that the capacitor should look like an open circuit, should look like a short circuit, which essentially means that what we are trying to say is the impedance of the capacitor should be much, much lesser than RL. Why RL? Why only RL? RL plus RD. Right? If I go around and write the KVL in the loop, I will have 3 drops. I will have drop across the capacitor, I will have drop across RD, I will have drop across RL. In the circuit on the left. In this case, I will have drop across capacitor plus drop across RD plus drop across RL. In the circuit on the right, I will have a drop across RD and drop across RL. And if these two have to be equivalent, we need to ensure that if these two have to be equivalent, we have to ensure that the drop across the capacitor has to be 0 ideally, but in reality, it has to be much, much lesser than the combined drop across RD and RL. Okay. If that is the case, which means that, when you have same current and we are only talking about voltage drops, we are essentially trying to imply a relationship between the impedances. And what is the relationship that we are trying to imply? That the impedance of the capacitor has to be much, much lesser than the resistive impedance in the network or resisting impedance in the loop. Correct? So in other words, what I'm saying is 1 over j omega naught C mod of that has to be much, much lesser than RD plus RL. Or in other words, what I'm saying, C has to be much, much greater than 1 over omega naught RD plus RL. Okay? Yes.
Why RD is coming into the picture?
Okay. So do you agree with the fact that this condition needs to be satisfied or no? So what is the drop, which essentially means that I am trying to minimize the drop across VC with respect to the drop across RD and RL.
RL is common to both the sides.
Correct. RD is also common to both the sides. right? Your RTR is here, RTR is here. Does that give an extra capacitance? We are trying to draw an equivalence between these, right? Okay, so now again, this is specific to this network, what we did. But let's say you have a network where you have, let's say you have a network. You have a whole bunch of resistances and control sources, right? But all resistive, let's say. Everything is resistive, no imaginary term. And you have a capacitance somewhere in the network, right? And I take the capacitance out. And I'm trying to figure out the value of the capacitance such that the value of the capacitance is such that it acts like a short circuit at signal frequencies at omega naught, right? So what is the algorithm? What should I look for? R out for
the DNS setup.
Okay. Somebody said RTH somewhere here. Right. So essentially what we are trying to figure out, very good. Essentially we are trying to figure out is that what is the equivalent Thevenin output resistance looking into the network. If we the reason I said it's everything resistive inside, because Thevenin, this impedance will always be resistive if everything stuff inside the network is resistive, which essentially means that I should be able to replace the stuff inside the network with RTH, and we'll have a capacitance here, and all we have to ensure is that C is much greater than 1 over omega naught RTH, right? Another way of the time constant, that is RTH times C, should be greater than 1 over omega naught. So this is tau, right? So again, these are circuit hacks. I mean, these are analysis hacks, because one can always write down the full-blown equation, find out the total transfer function, and then impose the condition. But when you are doing a design on the fly, you don't want to disrupt your thought process and always go back and find out what the conditions will be. So you should be able to look at the circuit network and figure out the constraint intuitively. And given any set of networks, assuming again it's a first order network, it should be pretty straightforward to figure out what the values of the capacitance should be. So if we want the capacitor to act as a short circuit and so on. And the hack is find out the Thevenin equivalent and then ensure that the time constant is much greater than something, right? What is something in this case is 1 over omega naught. Okay. Any questions? So this again, I mean, this again reinforces the importance of figuring out a Thevenin impedance, right? So you should be comfortable in finding out impedances, looking into the network, right? So the problem set 1 had the range of circuits where you had to find out the impedance, and you see that throughout the course we'll try to look into, we'll try to figure out the impedances of the network, looking in some terminal, looking out of some terminal, and so on, because that essentially will determine the characteristics of the network to a large extent. Okay, fine. So if this is satisfied, then let's go back to our analysis. So one good thing about putting a capacitor that I missed alluding to, one of you was pointing out that this capacitor has to be initially charged, right? If the capacitor doesn't have the initial charge, then there's no point in putting the capacitor. But what I mean, just putting the capacitor here, uncharged capacitor into this network, will it work, or do I need to charge the capacitor first with VDQ and then apply it here?
It will work either way.
It will work either way. Why?
After some time it will surely get.
Okay. So just like a capacitor acts as an open circuit, let's assume the capacitor was initially uncharged. Right? So let's assume you took a uncharged capacitor with Q equal to 0, that is V equal to 0 across the capacitor, and plugged it in here in the network as I have shown. What would have happened? So this capacitor would have been uncharged, right? VC would have been 0. Then what would have happened? Current would have flown in. Some current would have flown into this network, and it would have charged up the plates of the capacitor. And how long that charging would have happened? As long as the voltage across the capacitor reaches the quiescent state of the drain voltage, right? So one might argue that putting a capacitor is even better than putting a battery, because when you are putting a battery, you have to first calculate the quiescent state and then find out the value of the battery and then put the battery. Because if there is slight difference in voltages between the quiescent voltage at the drain and the battery voltage, then again current will flow either this side or that. But in case of a capacitor, you don't have to do that. The capacitor already will automatically figure out what is the value that is required, adjust its terminals, and act accordingly. So to some extent, the capacitor is even better than a battery in trying to figure out what voltage it naturally requires. Okay. Okay. How much time we have? We have 5 hours. Okay. So now that is as far as the output side of the network is concerned. If we turn our attention to the input side, now at the input side, we also have a problem, because just like we didn't have access to a floating battery, we also don't have access to a floating source, because the source might be coming from some previous stage, right? So the source might be some previous stage which is driving your amplifier, which means again you have access to one terminal, and the voltage across the terminal is reference to some common ground. Okay, so what I'm saying is this is not possible, right? So even when you are doing it in the lab, you normally see you have a big box of voltage source and you have another big box for battery, and you never connect them in series, right? Because it is assumed that the common terminals are always grounded. So this is not possible in principle. So now that we know that we have access to, we can mimic a floating battery. So what do you think is a feasible solution? So let's do step by step. Let's try to understand what should we do in order to get rid of these floating sources. What I essentially mean is, let me resketch this, then probably it will make more sense. What I'm essentially saying is you have this, and you have this. And I need to ensure that the total voltage across the VGS should be equal to VI plus VGQ. Given that I cannot put this two contraption in series. So now help me understand what should we do. Give me any idea. I mean, we can put anything anywhere, right? Okay, so I can connect one resistance between battery and gate. Why not connect the battery directly to the gate?
constant.
Right. So yeah, this is good. So if one might have initially said that we simply connect it directly, then I don't leave any room to connect the source, right? The voltage source, because VGQ will always be constant regardless of whatever I connect the voltage source. So this cannot be done. I think that's why he is alluding to the fact that we can maybe connect it through some resistance. Let's call this R1. So this is RS. Then what should we do? Now, I mean, this is fine as far as the VGQ is concerned. VGQ is established, and I have also not shorted the gate to source. So what else? What needs to be done? Yeah, speak up ideas.
Capacitor in series with RS.
Capacitor in series with RS. Okay, why capacitor in series? Why not simply connect? Why not simply connect? Is there a problem if I simply connect? Okay, biasing will get affected. That I agree. So let's just humor me for some time. So let's assume that this is I connect it like this. What will be the voltage here? VI times R1 parallel RS plus VGQ times R1 parallel. Sorry, what I'm saying. VI times R1 by R1 plus RS plus VGQ times RS by R1 plus RS. Okay, fine. So it seems like still I have, I mean, if I have to establish the value of, if I have to establish the voltage, some VGS, right? So let's say this, I want to establish VGSQ, then it seems like if I adjust the values of VGQ, RS, and R1, I should be able to establish that voltage, right? Right. If assuming this battery voltage is in my control, R1 is in my control, RS is not typically in your control, R1 is in your control, then looks like I should be able to adjust the voltage of quiescent voltage, right? And what about the incremental part? Is the incremental part fine? Incremental input is attenuated, it's reduced, right? It's still it's a fraction of the input, isn't it? So other way of saying the same thing is you are loading the input. Yeah. Right. Exactly, right? So if we don't want to attenuate, if I ensure that if R1 is much greater than RS, then this term is close to VI. But what is happening to the other term? The Q point is decreased for a finite value of VGQ. Now, one might say that I will raise VGQ again. Possible, yes. That definitely is a feasible solution. You might want to raise VGQ and also raise R1. Right? If you raise both to some really large value, then it is possible to realize VI to be coming directly across the gate to source voltage while not disturbing the quiescent. This is a feasible solution. But the impracticality of it is that this will require certain, this will require a voltage source which is normally, the value of the voltage source has to be large with respect to something. Correct? And very often the value of RS is also not in your control. So which means that you probably have designed your circuit for certain value of RS. And it might not work for some other value of RS. So that is the impracticality of it. Even more, the greater impracticality is, again, when you see your when you see any circuit, or you even in the lab when you go and test it, you see that you are given only one voltage source. You are not given multiple voltage sources, right? Essentially, you have only one source. So it's not as if you will get one VDD here, one VGQ there, and if you have another amplifier, you will have two sets of the voltage sources again. So you will be given one voltage source. So you have to derive everything from the single voltage source. So if this value of VGQ is different from VDD, which is almost always the case, right? So you'll have to derive the value of VGQ from VDD. Okay. Okay, I think we are overshooting, so we'll stop here. We'll start off from here in the next class.